Hi guys, sorry we jumped in halfway through the lesson, but find the volume of rotating square root of x across y is equal to 0. Okay, y is equal to 0. That means we are trying to rotate this graph in this way. Now, to help you guys draw a nice volume, you do a mirror image. Here's my mirror image. Because as we rotate it, you're going to end up with this shape here. Right? We're going to end up with a bunch of these little circle shapes. Guys fill in it? Now, my point is that to build this volume shape, we actually don't have a concept for doing it, but we do know how to find small shapes, like the shape of a circle. So let's take one circle here. Take a look at this one circle. How do I find the area of this one circle? Because that's the shape that we're using. We're using the shape of a circle. This area shape is pi r squared. To find this one circle shape, the area would be pi square root of x squared, because our r value is square root of x. That's the radius here. You guys still hanging in here? This is my r. And r seems to be bounded by this equation. Now, to find the whole volume, and let's say the volume we want to go is from some a value to b value. We'll call it a to b. We have a starting and stopping version. So the idea is here, we're going to make all these circles across this plane all the way up to b. So here's what we do, and it's actually pretty easy. We are adding circles. So the way we do that in calculus is we just use the integral symbol. The volume is equal to the integral of circles. How do we give these circles a volume? If you guys remember the equation for volume, volume is base times height from geometry. Our base is a circle. We just have to give this a little bit of height, a little bit of width, right? A little bit of width. Give it a little substance. How big do we want the substance to be? Do we want to be big chunky cylinders, right? Do we want big chunky cylinders? Nope, we want as thin cylinders as possible. So guess what? We're going to throw a little dx here. And this is our width. Or you can think of this as your base times height from A to B. And turns out, this is the formula for volume because we're just adding circles together. Let's go ahead and write it. Volume is equal to the integral from A to B of pi r squared, which are circles. And then we'll say dx here. Again, the variables are not the same. We're going to change r. R in our problem was the square root of x, because that's the distance from the axis of rotation to our edge, to our border. So we're going to go from, sorry, oops, wrong letter. V is equal to the integral from A to B, pi square root of x squared dx. Okay, and that is our equation. Oh, one more thing. We can simplify this by throwing pi on the outside because pi is a constant. A to B of square root of x squared dx. Okay, and that's how we find volume. This is the basic principle that we're going to be working with.
Wouldn't it just end up as x?
You're right. It would be if I simplify it. You're right.
Okay.
But the whole idea here is that ideally, you know, with quotations here, it's like the parentheses of a to b of f of x squared. Okay? But it's not always going to be straight f of x, because I'm going to do one skill here. I'm going to change it just slightly so you guys kind of are on point here. Is that what if I draw the same graph, say x squared of x, but rotate around y is equal to -3. It's almost like your jaw has now dropped. So we have our graph, square root of x, like we said before. But instead of rotating at 0, we're not doing 0. We're going to be down here at -3. I want you guys to try to think about, how does that change the shape of my circle? Is my circle going to be smaller or bigger? Has my radius increased or shrunk? Okay, so hopefully you guys are realizing my circle is going to get bigger. So my reflection is no longer here. This is not my reflection. My reflection is actually way down here. So I'm going to give myself another like 3 spaces here. And I'm going to draw my curve out here like that.
Wait, Mr. Ko, so why
Yes.
did you pick y equals -3? You just
This is
randomly-
just an example. Just an
All
example of me stretching out my circle to show you guys that.
All right.
This radius it flows right along what I'm expecting it to do. It's going to get bigger. Fine, I'm going to make the radius get bigger. So please take a look here. The one circle, I'm just drawing one circle here. And the radius now got longer. So this actually goes back to what we did before. Remember upper minus lower, right? This is the exact same idea, upper minus lower. Upper is square root of x. If I minus my lower, -3, that negative becomes a positive. So the radius is now square root of x minus -3 here. And it automatically makes that negative into a positive. So it's very similar to our upper minus lower from before. I'm not subtracting from top to all the way to the bottom. Remember, that's called the diameter. We're not using the diameter here, folks. We're just finding circles. And that's my new radius. So how does this equation change? The volume of this version is pi integral. Actually, no, let's write it the other way first. Integral of pi r squared, and our r squared here is going to be square root of x plus 3 squared dx. And please look at it, that's just a circle. Circle with a little bit of width gives us volume. And the integral allows us to add an infinitely many set of those. Okay, how do you guys feel about that? Pretty easy, yeah, right? And that's it. That's the whole concept. If you can get that, that's as hard as what these washers and shells are. Okay, well, these, discs, whatever these discs are. Okay. Now, this applies to any type of problem. What if I went ahead and spun this around? What if I gave you an equation, though, this time, and I said y is equal to x squared plus 2, okay? X squared plus 2 is a parabola, 2 spaces up, and here's your graph over here. If I spin this around the axis of rotation, let's say the axis of rotation, axis is y is equal to 0, easy peasy. Think about what type of shape do you end up with now. If I spin this out, give yourself a nice mirror image. Let me pick a different color so you guys can see it. Right? Flares out going this way, right? So it looks like kind of a bowl shape now. But does the formula change at all? What type of shape is still that quote-unquote base? The base is still a circle because when I rotate something, it always ends up in a circle. At least that one sliver. Remember, we're worried about the sliver. Oh, Mr. Ko, it's a bowl now. Do we have a different shape for a bowl? Look at that one base. The sliver is a circle, so we're still adding up circles. The volume is integral, add up circles. Give it a little bit of width, and we're done. The volume is pi r squared. What's my r value? My r value is x squared plus 2. And then you could say, well, it's x squared plus 2 minus 0. Fine, minus 0 doesn't matter for us. Okay, let's go back and let's share screen on this computer again. So we're looking at these types of models, and really we're taking our basically one shape model. Let's use so we're taking one, in this case it's a thick cut, right? But that's the idea. And we're giving ourselves a bunch of these added together. Okay? And when these slivers are small enough, we end up with a nice smooth curved surface here. Okay, let's see if there's anything else I want to use here. Slightly different. So what if we spin the other direction? If you take a look here, if you spin the wrong direction, you end up with a different shape. And this is the kind of idea of what we're going to do with shell method later. And there's a specific reason when we use shell and when we use our typical washers and disk. Isn't that pretty? Now, would you call this a washer or a disk? Remember, a washer has a hole.
Washer.
A washer, good.
Washer.
Only difference is that there's a hole in there's a hole in the middle. Okay? So how do we cut out that hole? I literally just said it. We cut out that hole. So the way we do these problems is you don't find just one volume. We find two separate ones that we subtract from each other. Okay? So we'll do the large volume first, and then we're going to minus the cylinder in the middle. And that's the next type of shape that we can create. In a sense, a subtractive method. Let's see, what's this one? And this is a shell method. So if we want to spin in a alternate direction, in this case, you see we're spinning around the y-axis. So that's another method. And we'll learn when we use which. Okay. All right. That's it. Folks, that is the lesson for today. So let me go ahead and share my screen one more time over here and give us just a couple more examples so you guys can get where I'm coming from. Give me 1 second. So your homework is going to be like ridiculously easy, like no joke.
All it is just setting up the problem.
That's it. Just to make sure you guys have your brain wrapped around it.
Like we don't have to do anything on a calculator or anything.
Nope, there's no, because everything else is just plug into a calculator. The hardest part is always setting up the model. Okay, so let's come up with another problem. Let's do something like this. Y is equal to negative x squared plus 1. All right, great. That's a parabola facing downward at 1. Okay. And then if I ask you to rotate around y is equal to 0. Okay, we're going to rotate around this. Rotate around y is equal to 0. Okay, so if you're looking at it, we're going from here to here. That's what we're going to rotate around, and then we'll make this shape like a circle here. I want you to rotate between the values of x is equal to 0 and x is equal to 1. Okay, we're going to start at 0 here, stop at 1. Okay. All right. We have everything we need to know. If we want to draw this nicer, like, what would the shape really have looked like? If I draw you a parabola coming down, this is where we're stopping from 0 to 1. You would end up rotating it, and you end up getting a little dome thing, right? This is what the 3D version would look like. Sorry if I broke your brain. Right? It looks like a bowl, upside down bowl. But see, if you think of it as upside down bowl, it makes the problem harder. Just think of it as a slice of a circle. And what's the radius of that circle? Because we're just adding layers of circles. Okay, the circle is pi r squared. Adding circles, pi r squared. Where r is the distance from the border of my function. In this case, it's negative x squared plus 1 to the axis of rotation, which is in this case 0. So the radius is just negative x squared plus 1 dx from 0 to 1. Okay, because I'm traveling from 0, my circles are going from 0, and we're walking our way all the way up to 1. 0 to 1. Okay, I forgot to write the square, sorry. Squared, pi r squared. Throw out the pi, 0 to 1 from negative x squared plus 1 squared. Easy peasy, right? What if I change the axis? If I say same exact problem except y is equal to negative x squared plus 1, but I want to rotate around y is equal to negative 4. Okay. So we have the same model. We said it's going to go this way. We'll say from x is equal to 0 to 1, like what we said before. Except my y value is down here at negative 4. Now, I'm going to do my mirror image just in my brain so I can see this. And then I think it's going to be... Go down this way. That's my mirror image. Oh, that looks terrible. Meh. And then okay. Oh my gosh, that looks so terrible. So what's my equation? We're still using basing off circles. So it's integral from 0 to 1 pi r squared. I'm going to throw the pi outside because I'm getting more used to this. And it's going to be negative x squared plus 1 minus negative 4. That negative becomes a positive 4. Hopefully you guys notice that. And we're going to have a pi integral 0 to 1 of negative x squared plus 5. Okay. Now, what if I change the axis of rotation so that we're above the model now? Okay, so what if I said our axis of rotation, our problem is y equal to negative x squared plus 1, and now this time our axis of rotation y is equal to, let's call this 2, right? Let's rotate around 2 now. So we draw the same graph. And here's my 1, here's my 0, right? Except I'm going to be at 2. Here's 2. Here's 2. Now take a look here. We are flaring up, aren't we? So the graph would look like this, going up. So we have a bowl going this way. Oh, that's a little terrible. Oh, darn it. Come on. You guys kind of see my bowl going on? Now, I want you guys to discover what this radius is. And take a look here. I don't want to use this equation here. I don't know what that is. But we do know the radius is the same from here to here, isn't it? So the radius is 2 minus the function. 2 minus the function. Okay? Because it's 2 minus whatever that value of the function is. And that gives us what's left over. What's left over is the radius. Okay, so take a look at what I just did here. I said upper minus lower. The reason why we want that positive number, right? So upper is 2 minus the lower, which is the function. So upper minus lower. This gives us 2 plus x squared minus, minus 1. Which gives us x squared plus 1. So we have our formula 0 to 1, pi on the outside, x squared plus 1 squared dx. The goal is to figure out what is your base shape. Once you know our base shape, we just find the area of that base shape, multiply by a little bit of width, and then we change that area into a volume.